Hi everyone, and welcome back to the channel. We all know that the CPU is the brain of our computers, our phones, and even our smartwatches. It's the engine that powers everything we do, from sending a simple text message to editing a higher resolution video. But have you ever stopped to wonder how this tiny, unassuming chip actually works? It's a world of mind-boggling complexity, but today we're going to pull back the curtain. Let's go deep inside the processor and explore the amazing secrets of the digital brain. First things first, what does CPU even stand for? It's the Central Processing Unit. Think of it as the command center for your entire device. If you were to open up your computer and look at the motherboard, you'd find this small square chip, often hidden under a large fan or heatsink. Now, here's where it gets truly incredible. Inside that tiny square, there aren't just a few components. There are billions, and I mean billions, of microscopic switches called transistors. These are the fundamental building blocks of all modern electronics. So, how do these billions of transistors do anything useful? They work together using a very simple language, the binary system. You've probably heard of it. It's just O south and 1 south. For a transistor, A1 means it's on, allowing electricity to flow, and A0 means it's off, blocking the flow. By arranging these billions of on and off switches in complex patterns, the CPU can represent numbers, letters, images, and instructions. Every single thing you see on your screen, every calculation, every single pixel is ultimately represented by a massive sequence of these O south and 1 south, all processed by these tiny transistors. Now, a CPU isn't just a chaotic jumble of switches, it's a highly organized structure with several key components working in perfect harmony. Let's break down the three main parts. First, we have the control unit, or CU. You can think of the control unit as the manager or the traffic cop of the CPU. It doesn't do any of the actual calculations itself. Instead, its job is to read instructions from your computer's memory, interpret them, and then direct the other parts of the CPU on what to do and when. It orchestrates the entire flow of data, ensuring everything happens in the right order. The second major part is the Arithmetic Logic Unit, or ALU. This is the real number cruncher of the processor. As its name suggests, it handles all the arithmetic addition, subtraction, multiplication, and division. But it also handles the logic operations. These are things like comparing two numbers to see which is greater, or checking if a certain condition is true or false. Every calculation, from figuring out the trajectory of a character in a game to rendering a complex 3D model, is performed by the ALU. It's the mathematical heart of the CPU. And the third key component is the registers. Registers are small, super-fast memory cells located right inside the CPU core itself. Why are they needed? Well, fetching data from the main computer memory, the RAM, is relatively slow from the CPU's perspective. It's like a master chef having to run to the pantry for every single ingredient. The registers act like a small spice rack right on the countertop. They hold the specific data and instructions that the ALU is working on at that very moment. Because they are so close and so fast, they allow the CPU to access information almost instantly, dramatically speeding up the entire process. So, how do these three parts, the control unit, the ALU, and the registers, work together to get things done? They follow a fundamental process known as the instruction cycle or the Fetch-Decode-Execute cycle. It's a continuous, lightning-fast three-step dance. In this step, the control unit reaches out to the computer's main memory, the RAM, and fetches the next instruction in a program's sequence. Step 2 is decode. It figures out what the instruction is actually asking for. Is it an addition problem? Is it a command to move data from one place to another? The control unit translates this binary instruction into a series of signals that the other parts of the CPU can understand. And finally, step 3 is execute. This is where the action happens. The ALU then performs the actual operation. It adds the numbers, compares the data, or does whatever the instruction told it to do. The result of this operation is then stored in a register or sent back to the main memory. This three-step cycle of fetch, decode, and execute happens billions of times every single second. It's the fundamental rhythm that powers all computing. Every time you move your mouse, type a character, or launch an application, you are kicking off millions of these cycles. Now, let us talk about some terms you've definitely heard when shopping for a new computer or phone: cores and clock speed. Let's start with cores. In the early days, a CPU had only one core. This meant it could only truly work on one task at a time. To give the illusion of multitasking, it would switch between tasks very, very quickly. But modern CPUs are multi-core. You've heard of dual-core, quad-core, or even octa-core processors. You can think of each core as an individual worker or a complete processing unit inside the single CPU chip. Each core has its own control unit, ALU, and registers. So, a dual-core CPU effectively has two brains. A quad-core has four, and so on. This allows your computer to perform true multitasking, dedicating different cores to different tasks simultaneously. One core might be running your web browser, while another handles your music player, and another manages background system processes, all without slowing each other down. More cores generally mean better performance, especially for demanding tasks like video editing, 3D rendering, and modern gaming. Next up is clock speed, which is measured in gigahertz, or GHz. A clock speed of 3 GHz, for example. means the CPU's internal clock ticks 3 billion times per second. With each tick, the CPU can perform one step of the cycle. So, a higher clock speed means the CPU can complete more cycles per second, and therefore process instructions faster. The efficiency of the CPU's architecture, how much work it can get done per clock cycle, is also critically important. Let's dive a little deeper into memory. I mentioned that registers are super-fast memory inside the CPU. This is called cache memory. Cache is a small amount of extremely fast memory that is also located right on the processor chip itself. Its job is to store copies of data and instructions that the CPU has used recently or is likely to need again soon. Here's how it works. When the CPU needs a piece of data, it first checks its fastest, smallest cache, known as L1 cache. If the data is their situation called a cache hit, it gets it almost instantly. If not, it checks the slightly larger and slower L2 cache, and then the even larger L3 cache. Only if the data is on 10, any of the caches a cache miss, does the CPU have to make the long, slow trip to the main RAM to fetch it. By keeping frequently used information close at hand, cache memory dramatically reduces the time the CPU spends waiting for data. Finally, let us touch on something you might see in the specs of a new processor: the manufacturing process. Described in nanometers, like 7 nanometers or 5 nanometers. What does this number mean? It refers to the size of the individual transistors on the chip. A nanometer is 1/1000th of a meter, an almost unimaginably small scale. The smaller the manufacturing process number, the smaller the transistors. First, if the transistors are smaller, you can fit more of them onto a single chip. And as we've learned, more transistors generally means more processing power and more features, like more cores or larger caches. Second, smaller transistors are more energy efficient. They require less power to switch on and off, which means the CPU generates less heat and consumes less battery life. This is why our phones can have such powerful processors without needing massive cooling fans, and why their batteries can last all day. The continuous shrinking of transistors, a trend known as Moore's law, is the driving force behind the exponential growth in computing power we've seen for decades. So, from the binary language of O South and One South spoken by billions of transistors, to the organized dance of the control unit and ALU, and the clever use of cores and cache memory, the CPU is a true marvel of engineering. It's a microscopic city, bustling with activity, processing information at speeds that are difficult to comprehend. The next time you click a button, open an app, Or just move your mouse across the screen. Take a moment to appreciate the billions of tiny coordinated operations happening inside your computer's brain to make it all possible. I hope this deep dive gave you a clearer picture of what's really going on inside your processor. It's a complex topic, but understanding the basics can really help you appreciate the technology we use every single day. If you found this video helpful and want to learn more about the tech that shapes our world, please give this video a like and consider subscribing to the channel. We have a lot more exciting content coming your way. Thanks for watching, and I'll see you in the next one.